Hello. Now we come to a lesson which discusses K-means and MapReduce parallelism using Python. And this follows up the previous lesson groups which discuss basic Python K-means and also MapReduce. As always, we're using clouds to solving data analytics. Here, K-means is data analytics, and Kmeans is a technology which can be used in many fields. We actually discussed mainly its use in recommender systems and related classification problems. So we've already introduced actually the code that does this. And when we did that, we took the built-in SciPy K-means and modified it to make it implementable in MapReduce. The same type of changes can be done in any language. This has nothing to do with Python. So we have this sequential program which is now modified, and it looks the following. This MapReduce is actually going to run sequentially. It's just structured as map followed by reduce, and it could be implemented in parallel. So as we have this overall iteration of a starting positions. Remember that had 1 through 20 in the examples we gave. We initialize the centroids to random points in the initial data set. Then we iterate until converge, where the convergence is done in the change in the distortion. Then now we have this little change in the algorithm, which we'll see in the Python code, where we call the map to find the association of points to the current centroids. And then we just do the first step in finding the centroids by summing over the point vectors. We don't do the final steps. And also, this map could actually run over the entire data set, but it's set up in the code to also run over part of the data set. And we do these partial calculations in the map for anything which requires some global summation. And the centroids are global and the distortion is global, whether it be a maximum distortion or a mean distortion. In the reduce step, we sum up the contributions to the centroids from each map. Then we divide by the number of points in the associated with this center, and then we get the real centroid. We do various bookkeeping associated with the distortion. We also do this, I mentioned in the sophisticated program, you get rid of zero-size clusters. And then we finally check the convergence at the end of the reduce step. If we're converged, we return. Otherwise, we broadcast the new centers to all the processes and continue the iteration. The code is shown here. And this code is available for you to look at the larger font size. It has both the map and the reduce steps here. The map is a call to K-means underbar map, which we'll go through on the next slide. And so we only set this up for just as an illustration for the two cases of parallelism 1 and parallelism 2. The interesting thing is we call the same function, K-means underbar map, for 1 or 2. We just call it twice if the parallelism is 2. This is a general feature of parallel computing. When you're doing parallelism, you often run identical codes in each of the parallel processes. They get different answers because they're operating on different data. And that's the so-called SPMD, single program. That corresponds to a single map program here, multiple data. So that's a fundamental approach to parallel computing. As a result of this, each core, we find the number of points in the clusters, the distortion summed over points in each cluster, maxed over points in the cluster, and total number of points in this particular segment. And then we also in the code book we have the actual centers. Then we take the center, and in the case of parallelism 1, we we come back and do some arithmetic here, but for the case of parallelism 2, we still need to do a little bit of work. We add the two code books together, we add the number of points in the clusters together, we add the distortions together, we take the max over the maximum in process 1 or process 2, and then we add the total number of points together. So now we have a set of parameters here, which should be the same as the setup here, because they're done over all points, not just the half of the points which are in the first map and the other half of the points in the second map. This is an example of a problem where you get load balancing them equal amounts of work in each process by dividing the data sets equally between the different processes. Here we have then we do the final arithmetic in the reduced process. Involves getting rid of zero clusters and dividing the candidate centroids by the number of points, because the centroids are the average positions. The key difference in this algorithm, as we want to add results of the different processes together, we do not do the division by the number of points. That is only done here after we've added the two processes together. So this final, that's why it's slightly different from the natural ordinary K-means algorithm. You have to identify things like this overall division by the total number of points, which is only done at the end. Here now we come to this def K-means underbar map, and as I say, it's actually a very similar to the ordinary K-means code. It's actually slightly simplified. Here we do the call to VQ, vector quantization, to associate the points. This is only the points in each process to the centers, or rather to the clusters. We calculate the sum of for the distortion, which is going to end up being the average distortion. We sum that up for the distortion, which is the maximum. We find the maximum value over the points, and then we run over each cluster, and we calculate in here the contribution to the cluster centers from each point, and that is say essentially the same as what was done in the original K-means code, the only slight difference being we don't do the division. And then we return these things here, which we already accessed in the previous slide.